Where does gravity come from?
Yeah, I mean, how do you get gravity?
How do you get gravity? You're playing with me, right?
No, because I've been reading this stuff.
Okay, but
They did tell me how you get gravity, but I forgot.
okay. Well, see, I'm going to give you simple answers to complicated questions.
That's what I need, because I don't understand what I'm reading.
But simple answer. Look, gravity comes from the fact that mass. This has mass. Okay, this has mass. Okay, and I can prove it to you because it's really hard to throw that. Okay, so there's mass in this thing as I try to throw it. I can't throw it too fast because it's very massive. Okay. Also, this mass has another property besides inertia. It has another property besides inertia. It's called gravitational mass. And it also has a property that it pulls all other things that have mass towards it at the same time that all other things that have mass are pulling it towards them. Okay. Those two kinds of properties of mass are not the same. One is called inertial mass. One is called gravitational mass. And there's no reason that this inertial mass should have the same gravitational mass, but it does. So the very fact that this has gravity is thanks to the fact that when the universe was invented by the property maker, the one who made all the parameters, okay? If you want to make that God, fine. But if you just think that maybe there is another universe in which, you like multiple universes, so in another multiple universe, the inertial mass is not the same as the gravitational mass. Maybe in that universe, the gravitational mass is less. Maybe in that universe, there is no gravity from an inertial mass. What makes this have gravity, you're asking? I don't know. Now, Einstein just went ahead and talked about it in his way, but he didn't explain it, you know. Then there's the Higgs boson, which
God particle.
the God particle, which is, by the way, a misnomer, and it said, there's a little particle called Higgs that gives this thing mass in the first place, and I guess they meant gravitational mass as well as inertial mass. But it is the Higgs that gives things mass. You could ask, that's to me as hard as any question. What do you mean a particle gives another particle mass? What, they hand it to it? Here, you can have some mass. You know, I don't need it, you can have it. Well, I don't understand why the Higgs gives stuff mass any more than anybody else does. I mean, except the people who, of course, make a living at it. What makes things have gravity? I really don't know. Seems like it's a proper thing. You should have gravity. But you really want to know, why does mass have gravity? I don't know.
In the article I read, something bends.
Yeah, you want to talk about bending space-time? God bless you. Mass bends space-time, okay? So the property of mass, that is all, the gravity isn't about a pull, okay? It's not about a pull. Einstein said, forget pulling. The mass doesn't pull. What it does is it bends space-time. That makes you happier? You want this bending space-time to have something to do with the fact that this falls? Good. This is falling because there's a geodesic, okay? The passive least resistance, which happens to be bent space-time, which is causing this to fall. Does that make it better for you? Doesn't make it better for me. You know, just because you redefine it, you redefine the force away and you talk about geodesics. Why did that get there? Yes.
But if you're in space, and if you're on the moon, then that specific gravity is not the same, because it's the same item with the same water inside it, but it doesn't have the same specific gravity, and it won't fall at the same rate.
It will. The gravity of this, okay, the gravity of this container of water is in fact a definable quantity. I can write the equation, if you like. I can write it here because I know it's simple. The equation for what the gravitational force that this exerts on the Earth. I can bring this to the moon. It will still have the same equation and exert the same gravitational force on the moon. Okay. However, the moon is not going to respond readily to the gravitational force of this bottle. Okay, because it's not impressed. Conversely, the moon has a gravitational force on this bottle. And this bottle will not move as quickly on the moon because this bottle is not impressed with the gravity of the moon. And this bottle is more impressed with the gravity of the Earth. So I made a parallel here, okay? You understand this? Did you see the fact that I said not impressed on both objects? Because they are, in fact, in working together. This pulls this pulls this. The force is this.
Oh.
That hurt.
With the bottle.
Put the bottle down. I hurt myself with the
put
other
it-
arm.
It's cold.
Put the cold on the piece of
No,
flesh that's burning.
This isn't that okay. This isn't that cold. I'll survive.
Better than nothing.
Better than nothing. I didn't break it,
Of course not.
but I will have a bump. So the gravity is both ways. It pulls on me, I pull on it, and it's the same sort of thing. Why this has gravity, why that has gravity, it's because it has mass. I can't answer the question, really.
Well, in a space vehicle, it will have no atmosphere, and it will stay in the air. If you drop it, if you let it go, it will stay right there, floating. So nothing is exerting a pull on it, or maybe if there is a pull exerted, it's a very negligible pull.
Okay, so you take this bottle, I will not smash it up and down. You take this bottle, you go up somewhere. Where would you like to go with this bottle? How far away from what? How far?
Let's say 10 feet.
10? How about
I don't know. I mean, in a space vehicle.
in a space field? How far up would you like to go?
On
Make up a
Earth?
number.
On Earth,
No, it's away from the Earth.
away from, let's say 40 miles.
40 miles. Okay, you still have gravity. Okay, so there's
But
plenty
much
of gravity.
less.
Not much less, actually.
Really, 40 miles?
No.
Okay.
Make it 500 miles.
500 miles. Okay, 500 miles. A little less.
A little less.
A little less. A little less. Look, here. It's why we're not children in this room. We've all been to school. We all can look at an equation, right? Good. So, so this is the force of gravity. The force of gravity is equal to big G, big M, for like the moon, small m, for like the bottle, over r squared, where r is the distance between the center of mass of those two objects. Okay? Now let's do the math. The Earth is 4,000 miles in diameter. 4,000 miles in diameter.
No, that
The Earth is 4,000 miles in diameter.
Okay.
In radius.
Oh, okay.
Radius, sorry.
Right,
Okay, that's r, radius.
right.
Okay? And now you want to add 40 miles.
Or 500.
Well, you started with 40.
Okay.
So you realize that that's 4,000 plus 40 squared. That's not much different. It's a bigger number than it was before, but f isn't much smaller.
Why
Okay?
is it squared?
Because that's the way, that formula is squared. That is the formula. That is, when Newton derived his theory of gravitation in 1600, that's what it looked like. It's still right. When we go to Mars and the rest of the planets, when we send spaceships around the solar system, guess what equation we use? We do not use Einstein's theory of gravitation. That's unnecessary. We use that equation. That equation is sufficient to get us anywhere in the solar system, period. Okay?
Better than a passport.
Better than a passport. So the thing is, you wanted to make it 500. So you wanted to make it 4,500. squared. That's a bigger number, but still, the force of gravity, still, if you look at 4,500 squared, is bigger than 4,000, but not by a lot. I said a little. You understand why I mean by a little now? It's not 14,000 is 16 something, okay, square, you know. And 4,500, well, I don't know, but I do know what 5,000 is, and that's 2,500, okay? So the difference between divided by 16 and divided by 25 is not that much. It's some, but it's not a lot. So you want to get someplace where there's no gravity. No gravity at all. Well, congratulations, there isn't a place in the universe which is missing gravity. Everywhere, a vacuum doesn't work. It's not about the vacuum. It's all about how far away are you from stuff. Okay, how far? Let's make something, I don't know, 25 million miles away. You know, let's pick something. There's a thing called the sun. Have you noticed? It's got planets that refuse to miss, and they don't. The planets don't ignore the sun. The sun is saying, you know what? I got you. Earth, 1 year around for you. Mars, 2 years around for you. How about Jupiter? 5 years around for you. Saturn, 10 years around for you. I got gravity. How far do you want to go before the sun doesn't have anything to say about the things that it's playing with? Because it's got a solar system out there that's filled with stuff. So you say, aha, well, I can go somewhere where there's no gravity. Let's go further. I'll leave the solar system. But you know what happens when you leave the solar system? There are other stars. The nearest star is 4 light years away. You think that maybe between here and there, if you go there, somewhere between here and there, there's no gravity? Of course there's gravity. It's just whose gravity is stronger. It's a competition.
But it doesn't exert an
It's
appreciable force.
So at some point you want to define appreciable. You want to define appreciable. What is appreciable force? Okay. So the thing is, let's make an appreciable force equal to 0, 1. Okay, maybe that's not 0, 1. I'm not going to give you what units that is because that's not the point. Point is 0, 1 somethings. Okay. You'll go, oh, that's appreciable. Okay, fine. How about 1.01? Is that appreciable? No. Tell me when I can stop writing zeros. Okay. Is this appreciable? Is this exactly at what point do you get to non-appreciable? Oh, how about there? Non-appreciable. Because there's no end. I'm going to put a 1 at the end of a string of zeros no matter how far out I go. There's gravity everywhere in the universe. There's just less of it. There's just less of it.
How about in the other galaxy?
Okay.
Can you reach my walker? I want to go away. You reach it.
So let's talk about a giant fraction of the universe, because it happens that I happen to have this one queued up. Okay? So when it comes to commercials. 3, 2, 1. Skip ad.
Delving into our home supercluster.
You don't need this.
I'm going to turn off the sound. Okay. This is a picture of the universe, our close by universe. And there's no way in this room that I can convey to you how big this close by universe is. But I can say a number, okay?
You mean galaxy?
I mean galaxy. From here to here might be 300 million light years. That sounds like a big number, and it is, but that the galaxies, the universe is bigger. So if this is 300 million light years, that's this much. It's the big universe is much bigger, but it's still a big piece compared to the piece that we're in right now, which is ridiculously small and not worth mentioning. This piece is what you call the largest piece of universe that we have ever given a name to. It's where we live. It's the giant neighborhood that we live in. The observations were done on the island of Hawaii. The name of the area of the universe that this is called Laniakea.
What is it?
Laniakea.
That's why, because it's Hawaiian.
Right. And what you're going to see when I press play in this video is you're going to see movement. You're going to see movement. And the movement you're going to see is the result of these galaxies pulling on each other so that because galaxies are big, much bigger than milk bottles, they're pulling on each other, and as a result they're moving with respect to one another. What you're going to see here is the flow of the galaxies in this space by the force of gravity that you think we can somehow get somewhere where there isn't any of. Okay? This is the universe as empty as it gets. Every dot here is a galaxy with 1 billion stars. Okay? And in this picture, the movement you see is of these billion galaxies probably in this picture executing a dance under the force of gravity.
Can I make
You can see
it?
that most galaxies are being pulled.
Can I make it any bigger? Yes.
This is known as the Great
Look.
Attractor.
Look at that. This is the direction that the galaxies are moving in under the force of gravity.
Let's take a different view.
These,
Each circle represents a galaxy.
I've suppressed the sound.
Again, we can
But I'll
see
put it
most
up.
galaxies being pulled towards the Great Attractor in the direction of the arrows. Between the Great Attractor and us, the Milky Way, is a relatively empty area, a blue void. And next to us is Virgo, a large and dense cluster whose bright galaxies have been observed from Earth for centuries. Until
Galaxies.
now, astronomers grouped us, the Milky Way and its surrounding galaxies, with Virgo and nearly 100 other clusters in a supercluster that stretches 100 million light years across. But using this new technique, we can see that this is just the tip of the iceberg. This cluster of clusters is merely an appendage of a much larger supercluster, more than 100 times bigger and more massive. But how did the team know?
So, where is there gravity? Where is there no gravity in the universe?
Wouldn't you never? Nowhere.
There's gravity everywhere. So, but the thing is, you were making a mistake that people would make at the same time that Einstein was around. Everybody was making more or less the same mistake that you were making. And Einstein said, wait a second, this is a stupid conversation, let's have a different conversation. And he took what you said, he turned it on its heels, and he invented the general theory of relativity. So you're right there asking almost the right question, but you have it wrong. And I'll turn it around for you, and if I can, in a few minutes. Yes?
Says we can only observe a tiny part of what we call the universe.
I have to repeat what you say louder because you're in the back, okay? Since we can only see a teeny part of what's in the universe. Observe.
A tiny part of the universe.
Right.
So how can we speculate that it's all the same? Might another part of the universe not have galaxies or be filled more with
So we can only see a teeny portion of the universe, but Barbara, you got here late as always, and you didn't see the opening picture on my screen. The opening picture on my screen looked like this. This is the universe, okay? Notice that the universe. See, you go and you look everywhere. So you look here, you look here. I didn't discuss this picture, okay? But for the purposes of your question, you're saying is, well, we didn't look here, and I'm saying, but we did. You say, well, we didn't look here. I'm saying, but we did. Where is it that you think we didn't look? So it might be hiding some surprises for us. You mean beyond this? Okay, because I tell you, this is not the universe, this is the observable universe. So if you're saying is beyond the observable universe, there might be something hiding. I always say clowns, okay? So there might be clowns hiding behind the user, and we wouldn't know, right? Because it's beyond the observable universe. So you're free to postulate clowns. I would be more likely to postulate more of the same. But yeah, it could be clowns, right? Right. So,
Send in.
what?
Send in.
Send in the. That's the whole point. That is where it comes from, right? So to answer what you so really to go where you were going, okay? Because it's really important. What are you trying to do? You eliminated air, but that didn't work, okay? You tried to eliminate gravity, but that didn't work, okay? You're trying for something, but I just told you you don't succeed. You can't get rid of gravity, it's everywhere, okay? What were you trying to do? Do you know what you were trying to do there? Where were you going?
I was trying to define, actually, not gravity, but force, like the great force and the small force, or the big force and the weak
You were
force.
trying to do, okay, force, goody. That's closer. It's excellent. I'm going to stop you there with force, okay? Now,
More than gravity.
okay.
More important than gravity.
right. This milk container, this water container, right? It's pressing down on my hand with a force, okay? If I let go, and I won't right now, the force of gravity is going to pull it down. What you want to do is you want to go somewhere where there's no force of gravity, okay? So that we can examine the situation when there's no force. You want to examine the situation when there's no force. But here's a force, so we have to leave here, clearly to be able to do the experiment that you were trying to invent in your head, someplace where there's no force. And I told you, sorry lady, no force, no place you can go. I always forget your name. Mario? Marion. Sorry, there's no place in the universe you can go where there's no force. And I expected you to walk away dejected and going, oh, really? Okay. Well, that does it for me. Okay? But Einstein had the same problem. He couldn't get anywhere where there was no force. So he said, you know what? I don't care. It doesn't make a difference. If I'm in a gravitational field, or I'm not in a gravitational field, where this imaginary place that you imagined, where there is no gravity, this imaginary place, well, Einstein went there in his head. He went there in his head and he said it's indistinguishable from being falling down in an elevator shaft, being in outer space, falling around the Earth. There's no way to distinguish those two conditions. That's what he said. That's what made him Einstein. That is the entire thing that made him Einstein. Once he said that, he was able to derive general theory of relativity. Anybody could do it. Anybody with a mathematical background could have done what he did with just that fact.
Explain that again.
Seriously. It's as simple as that. So you got close to where he was going, but he went the rest of the distance and said, I postulate there's no difference. In fact, I can't imagine that it's detectable. Think about it. It's not detectable. You can't determine if you're being pulled by a gravitational force a gazillion miles away from any stellar thing, or whether you're in orbit around the sun. If with your eyes closed, how would you tell? Einstein said, well, don't bother. It's the same. It's the same. And then it's really easy to. It's terribly easy to come up with Einstein's theory of general relativity. It's simple. Can I show you on the board? I've done this before.
I stood at the mouth of a volcano when I lived in Costa Rica, and I felt an enormous urge to throw myself in. and I know other people feel the same way when
Yeah.
they sit at the mouth or they stand at the mouth of a volcano. I don't know whether that's anything to do with gravitational force or pull, but I know it was very strong. I had to stop myself from rushing into the mouth of the
I
volcano.
do not think that that's gravity. I think I have another word for it. It's called insanity. It's close. It ends with ITY, but otherwise I don't think they're the same.
They call it what?
Insanity, not gravity.
Insanity.
Right.
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 Oh, God, marriage.
Right. Right. So, can I show you? I've done this before in this class, but I think it's magical that you can literally derive Einstein's theory of general relativity in front of a class of people average 80 or older, and they will buy it. Well, you maybe not you, but you're the youngest in the class, nevertheless. Following demonstration will actually come up with half of the theory of general relativity, and the other half I can wave my hands and do the rest. Okay? So you're in an elevator. Okay, and this is you in the elevator. And here there is a hole and another hole here. Okay, and here there is a flashlight sending in a beam of light. And now the flashlight sends in the beam of light, and it exits the hole right there because it's directed towards the other hole. Fine. Now, this is what I see if I'm in the elevator. But it turns out that this elevator is falling. See, because there's no such thing as stationary. So I didn't tell you anything about it, but now I'm telling you that the elevator is falling. So, as the elevator falls, the light, which travels in a straight line, is not diffracted. We're talking about vacuum of space here. There's nothing. The guy in this thing is wearing a spacesuit. Okay, right? As the elevator falls, this ray of light continues to go straight, like it always has. But by the time the ray of light, but by the time the elevator is here, the ray of light, it started, the elevator is now here. The light had to go to here in order for it to exit at this point. It started here, but I'm watching the elevator and I'm watching the light. And the light exits right here where he sees it exit. But I see that in order for it to exit, it would have to have bent downwards to keep up with the falling elevator so that the light got bent in order for it to fall out of the elevator at a lower distance. So the gravity is bending the light in order for it to exit the elevator at the appropriate distance.
What if it's a light that has intensity and integrity, such as a laser light, which has intensity for miles?
Yeah, no, in fact, let's use a laser light, because a laser light is really good because we can literally see it. In other words, if I'm in the elevator, okay, if I'm in the elevator and there's an atmosphere, and I take a green laser, okay, I take a green laser and I point it like that, I can see the light making a straight line. I'm inside the elevator. Now I'm outside the elevator, okay, and I'm looking at that same laser light. It would actually have a curve downwards. Of course, gravity of the Earth is very minor, so the curvature of a light ray and the gravitational influence of the Earth is extremely small. So it's not noticeable by a human being, because otherwise we're on the Earth. I got a green laser, and you'd think the green laser light would point downwards. It doesn't do that, but it actually is bending downwards. But do you understand what you were saying? Do you see how close to what you were wondering gets you closer to what Einstein was saying? It's not very far away. The only thing is that you thought there was a difference, and that if you went far enough, you'd be able to make the difference disappear.
So
Einstein said
it approaches nothingness, but it never gets to.
And even if
zero.
it doesn't make any difference. I just told you, first of all, I made fun of you by telling you there's no way that it can get to zero.
Right.
Okay, that was the first thing I did.
Right.
And then, and then I said, but don't even bother. Let's not even bother trying to make it go to zero, because we can just do this in a falling elevator on the Earth. We don't have to leave the Earth to do this. Just a falling elevator will do this for us, and we can invent Einstein's theory of general relativity based upon just the supposition that there's no difference between a falling elevator, weightless in a falling elevator, and an infinitely far away from every gravitational being that you could possibly be. Those two things are the same. You wanted to get infinitely far away. I said, not necessary.
Right.
You could be right here. All you have to do is be an Einstein.